So we've now looked at water from a chemical standpoint. So now, and then we've done some water activities in class. And so now we're going to look at what it means that water has these hydrogen bonds. So remember, last night we looked at, or depending on when you watch this, Thursday night, you looked at the fact that water is bent and therefore it is polar and therefore it has hydrogen bonds. And it's those hydrogen bonds that are really responsible for water's unique properties, which are responsible for life on Earth. So one of the things that the hydrogen bonds are responsible for in water is water's ability to stick to itself and then also stick to other things. So surface tension, such as when you floated the paperclip on the water. Paperclips are much denser than water. Normally they would sink, but if you angle it just right, you can get it to float, and that's because you can kind of see these little dents here under this water walker's legs. That's because water has this unique ability to stick to itself because of those hydrogen bonds. It keeps the water molecules stuck together. You can also see that in here in droplets of water. That's why water forms droplets versus spilling all over the place. If it's a small enough amount, certainly if you dump water on the floor, it spills. But what that's called is, so we know that is surface tension, right? The water has high surface tension, but that's also called cohesion. Here's my pen. So that's called cohesion. This actually isn't water. This is a picture of mercury. Mercury also has a high cohesion, but you can see that the mercury is sticking to itself and forming a bubble. Well, water also has a high cohesion. It's very cohesive, and so it sticks to itself, which again is why it forms droplets. It's why you have high surface tension. However, because it's polar, it also has a high what's called adhesion. It adheres to other things. So that's why you get like a meniscus here, okay? Because the water is actually sticking to the sides of this tube. That's why you get what's called capillary action, where water can be drawn up through fibers and tissues in trees and in plants, because it sticks to the walls of those veins, but then it also sticks to itself, so the water stays together as it's being drawn up in the tree or the plant. That's also why here we talked about the cohesion, but it's also adhering to the spider web. So those properties of being both cohesive and adhesive, or you could say experiencing cohesion and adhesion, are one of the unique properties of water. So another unique property of water is that it has a high specific heat, and this is also because of the hydrogen bonding. So specific heat, and you maybe learned this in the chemistry portion of physical science, but maybe not. Specific heat is the amount of energy it takes to raise 1 gram of water, or of a substance, any substance, by 1 degree Celsius. And you remember, energy is measured in joules. So water's specific heat is 4.18 joules per gram per degree Celsius. For every 1 gram and 1 degree Celsius, it's going to take 4.18 joules of energy. Contrast that to vegetable oil, which is less than half. So it takes less than half of the amount of energy it took water to raise 1 gram of vegetable oil 1 degree Celsius. And that's why in class you saw a difference, even though they were exposed to the heat the same amount of time and the same type of heat and the same amount of heat. That's why the vegetable oil's temperature changed by more, because each joule of heat can actually raise the temperature of the vegetable oil almost twice as much as the water. Now, that means water has what's called a very high specific heat, and the temperature of something has to do with its kinetic energy. But those hydrogen bonds, because they're holding the water molecules together, it's hard to get them to vibrate and move around as much, which is why water has the highest specific heat of any liquid that we know of. And what this does, essentially, is it prevents liquid water's temperature from changing wildly. Now, that's really helpful in our bodies. We are like 80% water, or 75% water. I don't know. I don't really care. But we're a lot water. This prevents the water, it helps our bodies regulate our temperature because we are primarily water. So our body temperature doesn't fluctuate wildly when it gets cold or when it gets hot, because water, which is what makes us up, doesn't fluctuate wildly. On a broader scale, or I don't know, humans are pretty broad, life is pretty broad, but if you look at climate, here's where we are. So this is Seattle right here. And we know in Seattle we have a relatively mild climate. It doesn't get too hot in the summer, it doesn't get too cold in the winter. And if you've ever been to eastern Washington, like Spokane, you know it gets really cold in the winter and really hot in the summer. And that has to do entirely with the fact that we are surrounded by all of this water. Okay, we've got the Pacific Ocean out here, but then we've got the Puget Sound here, and our air comes from this direction. This is the way the jet stream goes. And so the water actually keeps our temperature milder. But as that air goes across Washington State, it loses the mild quality that it has from being above the water, and then it can fluctuate more wildly. It can get really hot in the summer, really cold in the winter. If you look at the east coast of the United States, it's still mild-ish compared to, say, the Great Plains, the Dakotas, but it's a lot more extreme than Seattle, as if you compare like Boston. It's very similar latitudes, but that's because the jet stream, our air, goes west to east across the United States. And so that idea of specific heat of water, it not only keeps our bodies at a more moderate temperature, but it's actually directly responsible for our unique climate here in Seattle. So the other thing is, and we talked about this a little in the other notes, is the hydrogen bonds in water are responsible for water's ability to dissolve polar substances and form solutions. So maybe that's more that water being polar than the hydrogen bonds. It's not really the hydrogen bonds, but I was going with a theme. But because water is polar, it can form solutions with polar compounds. So this is salt here. So this would be the Cl. The chlorine ion is a lot bigger than the sodium ion. And going back to ions, so the chlorine ion has gained an electron, the sodium one has lost an electron. So it's a 1-to-1 ratio because it's a plus and a minus, so 1 plus for every 1 minus. And that's an ionic bond, and that's pretty strong, but when it gets into water, because water's polar, you'll notice all of the negative oxygens are oriented around the positive sodium, and all of the positive hydrogens. And when I say positive, I don't mean the actual atom is positive. It's not like the chlorine that actually is negative and has gained an electron. But remember, we're talking about water being polar. So this side of water, the oxygen side, has a negative quality, and the hydrogen side has a positive quality. But then the salt can't stay as its little crystal, and so it dissolves. And remember, we talked earlier about like dissolves like. So polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. So if you remember that solutions vocabulary, the solvent is the thing that's doing the dissolving, and the solute is the thing that is being dissolved. And we can talk about that more if you need a refresher on that vocabulary. But think about our world, which is like 75% ocean. Okay, so it's really important for these habitats that the salt can stay dissolved. If you've ever tried to keep tropical fish in a saltwater tank, getting that salt to water ratio and making sure the pH is balanced and all that is pretty critical and not easy to do. That's why so many people have freshwater tanks. So obviously this ability for salt to dissolve in water is responsible for a lot of habitat on Earth. But it's also responsible for compounds that dissolve in your cells and are transported across cellular membranes. So on a much smaller scale, that's also very important too, and we'll talk more about that when we get to cells. And then finally, water's hydrogen bonds are responsible for water expanding as it freezes. The hydrogen bonds keep water locked in kind of a crystalline structure that makes solid water larger than liquid water, volume-wise. And that's unique. Most substances contract, get smaller as they freeze. I want to say rubber is also an exception. I don't know where I heard that. But water is definitely, if not completely unique, pretty unique in that characteristic. And that's important. Here we have my city where I grew up. This is Chicago. And then this is Lake Michigan, one of the Great Lakes, and you can see some ice floating on top. Well, because solid water, ice, is volume-wise is larger than liquid water, it floats, it's less dense. And this is really important for a couple of things. The first thing is it allows the ice to kind of insulate the lake, to keep some heat in that water underneath the ice, which allows life to continue. It doesn't kill everything off every winter. But then the other thing that you kind of say, oh yeah, that's kind of obvious, but if you think about what would happen if it didn't happen, is that because that ice is then on top, in the spring when it starts to warm up and you start to get more sun, the ice can melt. Whereas if the ice sunk to the bottom, and if you've ever played with a candle and you like pick a piece of the candle off the side and drop it in the melted wax, you know that the wax sinks. That's because, as I said, most things contract as they freeze, and so they are denser than their liquids. If the ice were to sink to the bottom, in a deep lake like the Great Lakes, it wouldn't melt. And if it doesn't melt, then that's really going to screw up the habitat in that lake. And so that's a really important characteristic of water too, that it expands when it freezes, and very unique. Most substances don't do that. And finally, just a little aside, how soap works, because we've been using soap. We used it to clean the jar of oil and water. We used it to break the surface tension of the water. The way soap works is it has two sides. So this side, which this diagram is calling the tail, is nonpolar. Okay, this is the nonpolar end. And if you're interested in why it's nonpolar, again, I'm happy to go over that with you. But for now, it's good to know that it's nonpolar. So that's going to dissolve your oils, which water alone doesn't dissolve. But then soap has this end here that is polar. And so that is going to dissolve in the water. So in other words, this part of the soap binds to the grease and oil by dissolving, and then this part of the soap binds to the water, and then the whole thing gets washed off because this is one whole molecule. So this sticks to the oil, which wouldn't stick to the water, but then this sticks to the water, so it goes water, polar end, non-polar end, oil, wash the whole thing off. And that's how soap works, and that's also why soap then disrupts things like the surface tension of water. So please feel free to ask any questions in the comment section or in class. Have a good night.